Welcome friends, Igor is here, and in this video we will consider the traffic network models. We will take a deeper look into these models and I will show an amazing connection between loops and null spaces. Let's get started. I already covered basic traffic network models in one of the previous videos, so if you have not yet seen it, you might want to watch that basic video first and then come back to this more advanced video. Here, I will provide only a very brief overview of the traffic network models. Many discrete structures, for example the road structure in downtown, can be described by directed networks. In this case, the intersections correspond to the node of the networks, and the roads themselves correspond to directed edges or branches of the network that connect the nodes of the network. Traffic flows along the branches of the network, and usually our task is to balance the flow of the traffic. To help you get up to speed on this topic, let's consider a basic example of a traffic network. We have 4 intersections which correspond to nodes A, B, C, and D, and many one-way streets. The arrows on the branches in the network show the direction of the traffic flow. The numbers next to the branches show the rate of the traffic flow on the corresponding street. We are given the amount of external traffic, the traffic that enters the network, as well as the traffic that leaves the network, and our goal is to balance the traffic inside the network. The unknown quantities of the traffic flows inside the network are denoted by the variables x1, x2 through x5. To balance the traffic in this network, we look at each node at a time. We look at the rate of flow in to the node as well as the rate of the flow out of the node. These two rates must be the same. Equating the traffic flowing into each node with the traffic flowing out of each node, we get 4 equations, one equation for each node in the network. Please pause this video if necessary to make sure you can reconstruct this table. For the traffic flow to be balanced, all these equations must be satisfied simultaneously. Therefore, we have a linear system of 4 linear equations in 5 unknowns. We can represent this linear system in the matrix form if we denote its coefficient matrix by, let's say, A and its vector of constants by B. To solve this linear system, we construct the augmented matrix and we apply the Gauss-Jordan elimination algorithm to find the reduced row echelon form of the augmented matrix. From the reduced row echelon form, we see that columns 1, 2, and 4 are the pivot columns, therefore the variables x1, x2, x4 are the dependent variables. The other columns are non-pivot columns, and we see that the variables x3, x5 are the free variables. We solve each corresponding equation for its dependent variable, and we obtain the general solution of this linear system. This general solution involves 2 free variables, x3 and x5. This is where we would normally stop in the basic traffic network model, but now let's take this one step further and let's conduct further analysis of this general solution. In one of the previous videos, we established that the general solution of a linear system can be obtained as a particular solution of this linear system plus the general solution of the corresponding homogeneous linear system. Let me remind you how this can be done. We split the general solution vector into several individual vectors. In the first vector, we collect all free constants. In the next vector, we collect everything that involves the free variable x3. In the next vector, we collect everything that involves the free variable x5. In each of the 2 vectors which involve free variables, we can factor out the free variable using the scalar multiple operation. And now, the vector p, which is the vector of constants, is one particular solution of the linear system, which can be obtained by assigning 0 values to both free variables. And the vectors u and v, which are multiplied by the corresponding free variables, come from the null space of the coefficient matrix A. In fact, these 2 vectors form a basis for the null space of the matrix A. Let me now explain how these can be interpreted in the context of the original traffic flow problem. The vectors in the null space of the coefficient matrix A are solutions of the corresponding homogeneous linear system. Our original traffic network model would have resulted in the homogeneous linear system if all the external traffic was set equal to 0. In other words, the elements of the null space of the matrix A correspond to balancing the traffic in a network where we do not allow any traffic to get into the network as well as any traffic to get out of the network. Let's interpret what kind of traffic is represented by vector u, which is the first vector in the basis of the null space. In this vector, x1 is equal to 1, x2 is 1, x3 is 1, x4 is 0, and x5 is 0. This pattern corresponds to one single object traveling around the loop A, B, D. The vector v, which is the second vector in the basis for the null space, corresponds to the following pattern. x1 is 1, x2 is 1, x3 is 0, x4 is 1, and x5 is 1. This pattern represents one single object moving around another loop A, B, C, and D. As you see, it turns out that the elements of the null space of the matrix A correspond to the traffic that moves around the network in closed loops. You might ask, is there any practical purpose to considering traffic that moves around the loops? Suppose the street that goes from node D to node A is in really bad shape and we would like to temporarily close this street for pothole repairs. Is it possible? Can we close this street and yet still obtain a balanced network? Let's look at the particular solution vector P, which was obtained by assigning 0 values to both free variables. Yes, it is an impractical solution because it contains some negative flows, but we are going to modify it by including some loops. To close the one-way street that goes from node D to node A means to make the traffic flow along this street equal to 0. This requires adding the traffic rate of 400 to this branch. However, we cannot simply add traffic to one branch because that will imbalance the traffic in the whole network. Do you see how to add traffic to this network yet keep the balance? The answer is to add traffic along some loops. For example, the branch that goes from D to A is part of a small loop ABD. So let's add the traffic flow of 400 to each branch in this loop. In the language of solutions of linear systems, we are adding a scalar multiple of the vector u by 400. The vector u comes from the null space of the matrix A, and it corresponds to one single car moving along this loop. Now we have a particular solution which does achieve our purpose. We have closed the branch that goes from D to A, yet the traffic in the entire network is still balanced. Encouraged by our first success, we decide to become more ambitious. Suppose we want to close two streets for traffic. First, the branch that goes from A to B, and second, the branch that goes from C to D. In other words, we would like to find a solution that balances this traffic flow such that x2 is equal to 0 and x4 is equal to 0. Let's start as always with our impractical particular solution, and we will try to modify this solution by including some loops. First, notice that the branch that goes from C to D is part of only one loop. It is the big rectangular loop A, B, C, and D. So to make the traffic from C to D to be equal to 0, we need to subtract 100 from this branch, and to keep the traffic in the whole network balanced, we need to subtract 100 from the entire loop. This loop corresponds to the vector v, so therefore we subtract a scalar multiple of the vector v by 100 from this one particular solution P. This achieves one of our two desired goals. We made x4 equal to 0. But x2 is not yet equal to 0. It is equal to negative 400. To make the traffic from A to B equal to 0, we need to add the traffic of 400 to this branch. But then again, adding traffic to only one single branch might violate the balance of the entire network, and to keep the balance, we need to add the same traffic to one whole loop. But now, we cannot add this traffic to the big rectangular loop because that will change the traffic from C to D. However, we still have a second loop, a smaller loop, ABD, which does not include the branch from C to D. So let's add a traffic of 400 to the small loop. In the language of solutions of linear systems, it means we're adding a scalar multiple of the vector u, which corresponds to the loop ABD, to the previous solution. Now, both x2 and x4 are equal to 0. However, the solution we obtained is not a practical solution because we have negative flows from D to A and from B to C. Therefore, it is impossible to close two streets AB and CD while keeping the same traffic pattern in a network. Do you see what needs to be done? We just need to reverse the traffic flow in these two branches. So, if you want to close two streets for repairs, AB and CD, then we also need to temporarily reverse the direction of the traffic into other streets. If you found this video useful, please give it a like to let YouTube algorithm give others a chance to discover this video. And subscribe to this channel if you want to see more of these videos. I hope to see you later, infinitely many times. Have a great day.